Section 7.4, area and arc length and polar coordinates. So if we talk about the area of a sector first, it's this right here. So this is the area of a sector. And what we're going to do with this is we're going to develop how we actually come up with the integral for using polar. So if you think about finding the area of this entire curve here, we could essentially draw these triangles, okay, and we could find the area of each of these. And then if we look at each individual area of those sectors there, each one would essentially be AI equals 1/2 theta and then r squared. Now again, these would be modified as well, this theta and this r here. And we know r is actually equal to, and I'm just going to write this out below, r equals f theta. So what we're really looking at here is for this AI, as we're looking for 1/2 theta, and then this is going to be an f theta squared. Now that theta is going to change as I continue to go around. So this theta is actually going to be my change in theta. And this is actually going to be my theta I. So now what I really get here for this AI, meaning the ith sector, I'm going to get the 1/2 change in theta f theta I squared. So then what that's going to do is I'm going to want to sum all of those up. So now if I write this as a sum, so I equals 1 to n, I'm going to get that 1/2 change in theta f theta I squared. And then if I think about taking that as these n's get really small, so as I cut these more and more and more and more and get more and more sectors in there, which means I'm going to squeeze them down to 0 here. So each sector is going to be a line. It's going to fill in the whole space there. And that's really just the limit of this as n goes to infinity. So then this right here is what the integral does. So when I talk about that integral now, so the area of that integral completely is going to be the integral. I have the 1/2 here. And this is from alpha to beta, doesn't matter. And then I'm going to end up with f theta squared. And this change in theta is now going to be my d theta. So this is the actual formula that we're actually dealing with here. Another way I can write this formula is 1/2 the integral from alpha to beta is r squared d theta. Because remember here, r equals f theta. So I can write it as an f theta squared or an r squared. Honestly, the best way to remember it is using this one here because r is just f theta, if I understand that. So that's the formula we're going to use when we're talking about area. So we're going to have to understand the direction of our graph even. Do you guys remember in the other video, if you've seen it, I specified, hey, it's going in this direction. Now the reason why is I have to know what direction I'm going in order to talk about my bounds here, to determine, hey, what's my upper bound, what's my lower bound, where do I start, where do I stop? So I'm going to have to understand in terms of theta where I'm starting and where I'm ending. So that's going to be the important thing for us in these problems here. The setup's going to be pretty traditional because it's just a formula. The more difficult side of this is going to be coming up with the bounds for these. So let's get started with some problems now in the next video.